video, let us see force between two long current carrying conductors. So here two conductors are there. First conductor W1, W2. In this there is a current I1, in this there is a current I2. You know that when a current is passing through a conductor, there will be a magnetic field. So this is a magnetic field because of the current in the first wire. You know the magnetic field due to a infinitely long straight conductor carrying current, that is B1 is equal to mu 0 I1 divided by 2 pi r, where r is the distance. Here, magnetic field here. Then minus I cap. Here, this is the x-axis. This is the x-axis, y-axis, z-axis. Then direction of the magnetic field is given by right-hand rule. So when current is upwards, hold the conductor in your right hand such that the thumb is in the direction of the current. Then the fingers will give you the direction of the magnetic field. So here magnetic field is directed into the board. That means it is along the negative x-axis. This is a positive x-axis, negative x-axis. Then unit vector along the x-axis is I cap. Since it is negative x-axis, minus I cap. So it can be written like this, minus mu 0 I1 2 pi r I. Then you know that when a current carrying conductor is kept in a magnetic field, it will experience force, that is magnetic Lorentz force. So now this conductor is kept in the magnetic field produced by this current in the first conductor. So that is acting in inward. Then magnetic Lorentz force df vector is equal to I2 dl vector. So we consider a small element of this dl, idl vector cross B1. B1 is the magnetic field produced by this conductor. Current flowing through this conductor. Because of the current flowing through this conductor, there is a magnetic field that is directed into the board. Now I2 dl vector cross B1. Now dl vector can be written as dl into k cap because current is in the upward direction. So then unit vector along the z-axis is k. So dl vector, here we have to consider this conductor. Here this is the dl. Here this is the dl. Since it is in the upward direction, dl vector can be written as dl k cap cross. For B1 you can write this minus mu 0 I1 I cap divided by 2 pi r. Then this negative sign is written at the beginning. Then mu 0 I1 I2 then dl divided by 2 pi r, then k vector cross k cap cross I cap. K, it is along the z axis, k cross I. So k cross I, it is along the y axis, k cross I. Unit vector along the y axis is j cap. So k cross I is j cap. Now you got to the force experienced by this conductor by a small current element dl. You divide by dl. Both sides you divide by dl, or you bring the dl this side. So you will get a minus mu 0 I1 I2 divided by 2 pi r j cap. Then we can write f by l. Instead of df vector by dl, we can write f by l is equal to minus mu 0 I1 I2 divided by 2 pi r j cap. This is a force per unit length on this conductor for force per unit length minus j cap. J cap is that side, minus J cap, so force per unit length will be acting this side. Similarly, we have to find the force experienced by this conductor. For that, we have to get the magnetic field here because of this current. So field here because of the current in this conductor, B2 is mu 0 I2 divided by 2 pi r I cap. Because here current is in the upward direction. See, here fingers are outward. So here magnetic field will be directed outward. That means positive x-axis. So I cap. Then this conductor will experience a force. Then that can be got from this relation df vector. You consider a small elemental length current dl vector, then I1 current in this conductor, then magnetic field here because of this current is B2 directed outward. So dl vector can be written as dl k cap because it is directed along the positive z-axis k cap. Then for B2 we can write this mu 0 I2 divided by 2 pi r I cap, and this can be written rearranged and written like this: mu 0 divided by 2 pi r I1 I2, then dl k cross I. K cross I is J. This is K cross I. K cross I is J. J cap. Now this is the force acting on as element of length dl. Now you divide by dl. When you divide by dl, you will get the force per unit length. So both sides, when you divide by dl, this dl will get cancelled. So you will get like this. Then df vector by dl, it can be written as f by l. So this is the force per unit length on this conductor that is directed towards this side. You can see minus j cap, but here you can see plus j cap. So it is opposite. So the force on this conductor because of the current in this conductor is directed that side. So here you can see currents are in the same direction. When currents are in the same direction, there will be attraction. Suppose the currents are in the opposite direction, current in this conductor upwards, current in this conductor downwards, then there will be repulsion. So this is the force experienced by this conductor, force per unit length. It is acting along the negative y-axis. So this is the force experienced by this conductor. It is acting along the positive y-axis. So here minus j cap, here j cap. So this is the magnitude of the force per unit length. Now suppose I1 is 1 ampere, I2 is also 1 ampere, distance between the wire is 1 meter. Then we can substitute I1 is 1, I2 is 1, then distance 1, then pi will get cancelled, 4 and 2 after cancellation 2 into 10 raised to minus 7. If the current in these two conductors are 1 ampere and distance is 1 meter, force per unit length is 2 into 10 raised to minus 7 Newton per meter. From this we can define what is 1 ampere. Suppose I1 is 1 ampere, I2 is 1 ampere, then distance between the wire is 1 meter. Now you substitute I1 1, I2 1, or 1, then 1. Then after cancellation of this pi and this 4 and 2, you will get a 2 into 10 raised to minus 7. So now we can define what is 1 ampere. 1 ampere is that constant current which when flowing through two infinitely long straight conductors kept at a distance of 1 meter in vacuum experiences a force per unit length of 2 into 10 raised to minus 7 Newton per meter.